What if the most profound message you ever received was not written in words, but in stone? For all of our history, we have gazed into the cosmic ocean, a civilization on a solitary island, wondering if other shores exist. We have listened with our radio telescopes for a whisper, a signal, a sign that we are not adrift and alone in this silent, sprawling universe. We have sent our own messages in a bottle, golden records and radio waves flung into the void with the desperate hope of a castaway. But we never truly expected the ocean itself to send something back. Not a signal, but a piece of driftwood. A visitor from another shore. A tangible object, forged in the heart of an alien star system, sent tumbling through the interstellar dark for millions, perhaps billions of years, only to find its way by sheer impossible chance to our little island of light. This is the story of such a visitor. A story that began not with a bang, but with a flicker. A faint streak of light in a telescope, a ghost moving where nothing should be. For centuries, we believed our solar system was a closed garden, its contents born from the same primordial cloud of gas and dust as our Sunday. Every planet, every moon, every asteroid, and every comet was a member of our family, a native of this celestial home. The idea of an object from another star system actually entering our own was the stuff of pure speculation, a theoretical possibility so remote that most astronomers never expected to witness it in their lifetimes. The distances between stars are so mind-bogglingly vast that they defy human comprehension. To cross that chasm, an object would have to be ejected from its home system with incredible force, travel through the frozen emptiness for eons, and then happen to intersect with the infinitesimally small target of our solar system. The odds were, to put it mildly, astronomical. And then, on October 19, 2017, the impossible happened. It was named Oumuamua, a Hawaiian word, meaning a messenger from afar, arriving first. And it was a messenger unlike any we could have ever imagined. It wasn't a sphere like most asteroids. It wasn't a dirty snowball like most comets. From the scant data we could gather as it sped past us, it appeared to be bizarrely elongated, perhaps 10 times longer than it was, wide, tumbling, end over end like a cosmic cigar or a shard of galactic shrapnel. It was dark, reddish, and utterly inert, reflecting almost no light and showing no signs of the classic cometary tale of gas and dust we would expect from an object heated by our Sunday. It was a phantom, a whisper of a thing, detected only because it passed so close to us, a mere cosmic hair's breadth from Earth. We had just weeks to study it before it vanished back into the interstellar night, forever beyond our reach. Our telescopes scrambled, a fleet of eyes across the globe, swiveling to catch a fleeting glimpse of this apparition. What we saw only deepened the mystery. Oumuamua was moving too fast, far too fast to be bound by our sun's gravity. It had fallen into our solar system from above. The plane of the planets executed a hairpin turn around the sun and was now rocketing back out its trajectory, a perfect hyperbola, the telltale signature of an unbound interstellar traveler. But there was something else, something that baffled physicists and sent ripples of astonished debate through the scientific community. It was accelerating. After whipping past the sun, as it began its long journey back out into the void, it was gently but unmistakably speeding up, pushed by a force we could not see and could not immediately explain. A comet gets its push from outgassing as solar radiation vaporizes its ice, turning it into a tiny celestial rocket. But Oumuamua had no tail, no coma, no visible evidence of outgassing whatsoever. So, what was pushing it? The question hung in the air, heavy and unanswered. Speculation ran wild, from hidden pockets of frozen hydrogen burning off invisibly to stranger, more exotic ideas. Some even dared to whisper the most tantalizing and terrifying possibility of all, that the strange acceleration was the result of its unnatural shape, that it was a thin solar sail-like object pushed by the pressure of sunlight itself, an artifact. A piece of alien technology tumbling silently through our home. While most scientists dismissed this as an extraordinary claim, lacking extraordinary evidence, the fact that it was even seriously considered speaks to how profoundly Oumuamua had shaken our understanding of the universe. It was a ghost that haunted our theories. It proved that interstellar objects were not just a theoretical possibility. They were real, and they were weirder than we had ever dreamed. We were left with a handful of blurry data points and a universe of questions. Oumuamua was gone, a tantalizing puzzle that had vanished before we could even begin to solve it. We resigned ourselves to the fact that we might not see another visitor like it for 100 years, or even 1,000. We had been given a glimpse through a forbidden door, only to have it slammed shut in our faces. We were wrong, so profoundly, beautifully wrong. Less than 2 years later, it happened again. In the late summer of 2019, a Crimean amateur astronomer named Gennady Borisov was scanning the skies with his homemade telescope when he spotted a fuzzy, indistinct smudge. Initially, it looked like any other newfound comet, but as professional observatories turned their more powerful eyes towards it and as mathematicians began to plot its course, a familiar sense of disbelief and exhilarating shock rippled through the world of astronomy. The orbital calculations were unmistakable. Its trajectory was another perfect hyperbola, even more extreme than Oumuamua's. This was not a member of our solar system family. This was another one, another traveler from the abyss. This time, however, things were different. We had found it on its way in times not on its way out. We had months, even years, to study it. And unlike the sterile, enigmatic silence of Oumuamua, this visitor, eventually designated 2I. Borisov was behaving exactly as we expected an interstellar comet to behave. It was a dirty snowball, just like the comets from our own Oort cloud. As it neared the sun, it grew a magnificent coma and a long, streaming tail of gas and dust. It was a fossil from a distant star system, and by studying its chemical composition, we could, for the first time, analyze the raw building materials of another solar system. It was a stunning confirmation of a beautiful idea that the chemistry of life, the water and organic molecules found in our own comets, was likely universal. 2I, Borisov, was a comforting discovery. It reassured us that the laws of physics and chemistry were the same out there as they are here. It was alien yet familiar. It was the discovery of a lifetime, and it should have been the end of the story for a while. 2 interstellar visitors in 2 years was an unbelievable stroke of cosmic luck. The universe had delivered its messages, and we were busy decoding them. We assumed we were entering a new, quieter era of study. But the universe, it turns out, was not done with us. It had saved its greatest, most perplexing riddle for last. And this time the messenger wasn't just passing through. This time it seemed to have a destination. This time it was taking aim. The discovery was made by the Asteroid Terrestrial Impact Last Alert System, a robotic survey program, more commonly known as ATLAS. Its job is to scan the entire sky every few nights, looking for moving objects, specifically asteroids that might pose a threat to Earth. In the mountain of data from late 2020, its algorithms flagged another faint traveler. At first, it was catalogued with a provisional, unassuming designation. It appeared cometary, but it was extremely faint, a barely perceptible smudge on the deep black canvas. As more observations were collected over the following weeks and months, a preliminary orbit was calculated. The numbers that came back were once again shocking. Hyperbolic, unbound. It was number 3. The third confirmed interstellar object, 3I, Atlas. The astronomical community, once stunned by a single visitor, now found itself in an entirely new reality. The gates were open. The interstellar highway was apparently far busier than anyone had ever predicted. But as the orbital data for 3I, Atlas, was refined, As its path was traced with ever-increasing precision, a strange and deeply unsettling pattern began to emerge. It was a pattern that didn't make sense. A pattern that seemed too deliberate, too perfect to be the result of random chance. Both Oumuamua and 2I, Borisov, had treated our solar system as a gravitational obstacle to be navigated. They came in from high above the ecliptic plane, swooped around the sun, and were flung back out their paths, dictated by the simple, elegant laws of orbital mechanics. Their encounters with our planets were fleeting and incidental. 3I, Atlas, was different. Its trajectory was not so simple. It was coming in at a much shallower angle, much closer to the plane where the planets themselves orbit. And as the simulations ran forward in time, tracing its future path through our solar system, scientists saw something that made them run the calculations again, and again, and again, because they couldn't believe what they were seeing. The new visitor was not on a simple, clean path around the Sunday. Its trajectory was taking it on a direct, unswerving, and breathtakingly precise course for the most powerful gravitational player in our solar system after the Sun itself. It was aiming for Jupiter. This was not a near miss. This was not a glancing blow. The calculations showed that 3I, Atlas, was on a path to fly so close to the gas giant that it would pass deep inside the orbits of its innermost moons. It was a celestial thread, the needle maneuver across trillions upon trillions of miles. The precision was staggering, almost unbelievable. If you were to stand on its home world in a star system we have yet to even identify and throw a rock across the galaxy, you would have a better chance of hitting a single specific grain of sand on a beach on Earth than you would of achieving this trajectory by accident. A random object ejected from a distant star hurtling through the galaxy for millions of years, buffeted by galactic tides and stellar winds, should not be capable of such a thing. It was a cosmic impossibility that was against all odds happening. The question, the one that kept astronomers awake at night, the one that filled whiteboards with frantic equations and fueled hushed, excited conversations across continents, was no longer times what times is it, but times why Jupiter. Why this planet, and why this exact surgically precise trajectory? Was it the most stunning coincidence in the history of science? A 1 in a trillion shot that we just happened to be here to witness? Or was something else going on? Was there some unknown dynamic, some subtle and previously misunderstood law of galactic motion that could shepherd an object from one star system to another with such incredible purpose? Initial theories were quickly found wanting. A simple gravitational assist where an object uses a planet's gravity to alter its course couldn't explain the sheer improbability of the initial approach. For a gravity assist to work, you have to arrive in the right place at the right time. 3I, Atlas, appeared to have solved that problem before it even entered our solar system. It was as if it had been aimed, but aimed by what no natural force we knew of could account for it. The object itself was faint and appeared to be a simple, inert piece of rock or ice, much like Oumuamua, showing no signs of propulsion or course correction. It was a ghost ship, silent and dark, yet it was navigating the treacherous currents of our solar system with the skill of a master pilot. The enigma of 3I, Atlas, presented us with a stark and chilling choice. Either our understanding of celestial mechanics was fundamentally incomplete, or this object was not a product of blind chance. It was a puzzle box delivered to our doorstep, a mystery that promised to rewrite our books on how planetary systems interact, and perhaps much more. The object was still years away from its rendezvous with Jupiter, a slow-motion enigma crawling toward its climax. We had time. Time to watch, to study, to theorize. We had to solve the riddle. To understand its impossible journey, we couldn't just look at where it was going. We had to look at where it had been. We had to become cosmic detectives, tracing its path backwards through the darkness, across the interstellar void to find its origin, its home. We had to uncover the story of its ejection, the secrets of its native star system, in the desperate hope that it would hold the key. The answer to why 3I, Atlas, was aiming for Jupiter was not to be found in our own backyard. It was waiting for us light years away, hidden in the biography of a star we had yet to meet. And when we finally found it, the truth would prove to be more astounding, more elegant, and more revolutionary than any of us could have ever dared to imagine. It would redefine not only the life of this one lonely traveler, but the very connections that bind the galaxy together. What if the great silence of the cosmos is not a sign of emptiness, but of patience? For generations we peered into the deep, listening for whispers from other worlds, scanning for artifacts of distant intelligence, yet the universe remained, stubbornly, profoundly quiet. Our solar system felt like an isolated island, a self-contained celestial clockwork, adrift in an impossibly vast and indifferent ocean. We were the sole proprietors of this small sunlit harbor, and while we could gaze out at the distant storms of nebulae and the lighthouses of other stars, we believed nothing from that outer darkness could ever drift to our shores. The laws of gravity, we thought, kept star systems apart, each a self-governing kingdom of worlds, forever separated by the tyranny of distance. The idea of a visitor, a physical object, forged in the crucible of another sun crossing that gulf, was the stuff of speculative fiction. It was a ghost story. Astronomers told themselves a theoretical possibility, a mathematical curiosity, but not something you ever expected to see. Not in our lifetime. Not ever. The universe, we had concluded, did not make house calls. And then on a quiet Hawaiian night in 2017, the universe knocked. It wasn't a thunderous arrival. It was a phantom, a barely there smudge of light streaking through the digital net of the Pan-STARRS telescope. At first, it was catalogued as just another asteroid, another piece of local rubble. But as astronomers plotted its course, a chilling, thrilling realization began to dawn. This object's path made no sense. It was moving too fast, far too fast to be a member of our solar system. Its trajectory wasn't a gentle, looping ellipse, the familiar dance of a planet or an asteroid bound to our sun. It was a hyperbola, a fierce, open-ended slash through our cosmic neighborhood. It had come from the interstellar dark, and it was heading back out, a transient guest, on a journey of millions, perhaps billions of years. We named it Oumuamua, a Hawaiian word for scout, or first distant messenger. The name was poetic, but the object itself was a profound, maddening enigma. It was nothing like we expected. It wasn't the icy, glowing comet that theory predicted would be the most likely form of interstellar traveler. It gave off no gas, no dust. It was dark, reddish, and inert. From the faint pulses of light reflecting from its surface, we tried to build a picture of this messenger. What we saw was impossible. It appeared to be extraordinarily elongated, perhaps 10 times as long as it was wide, a cosmic cigar or a shard of some larger shattered body. Stranger still, it was tumbling chaotically, spinning on multiple axes like a carelessly thrown stick, a wounded thing careening through the void. But the final confounding mystery was its motion. As it looped around the sun and began its outbound journey, Oumuamua accelerated. It gently, inexplicably pushed away from the sun with a force that gravity alone could not explain. For a comet, this would be normal. The sun's heat would vaporize its ices, creating jets of gas that act like tiny rocket thrusters. But Oumuamua had no tail, no coma, no outgassing. It was a ghost ship pushing against a solar wind with invisible sails. The mystery deepened with every observation, and the questions it posed struck at the very heart of our understanding of the cosmos. Was it a new kind of natural object, a hydrogen iceberg peeling away in layers invisible to our instruments? Was it a piece of cosmic shrapnel from a planet torn apart by a distant star? Or was it, as some dared to whisper, something else? Entirely. A piece of technology, an alien probe, silent and derelict. We scrambled every telescope we could, pointing our most powerful eyes at this fleeting visitor. But we were too late. Oumuamua was already faint, already racing away into the black, taking its secrets with it. It was a single cryptic sentence from an unknown language, overheard once and then gone forever. It left behind a trail of unanswered questions and a seismic shift in our perception of the universe. The island was no longer isolated. The ocean was not empty. For 2 years, the silence returned. We were left to debate the nature of our single ghostly visitor, wondering if it was a once-in-a-civilization event. And then it happened again. In the late summer of 2019, an amateur astronomer in Crimea, Gennady Borisov, pointed his homemade telescope to the sky and found a fuzzy blot of light moving with purpose against the stellar backdrop. This time, the astronomical community was ready. Within hours, the global network of observatories was alerted, and the world's telescopic gaze converged on the newcomer. The orbital calculations came back quickly, and they were definitive. Like Oumuamua, this object was unbound. It was another traveler from the stars. But this visitor, designated 2I, Borisov, was profoundly different. It was exactly what we had been expecting all along. As it drew closer to the sun, it began to glow, sprouting a magnificent ghostly tail of dust and gas. It was without a doubt a comet, a perfectly, wonderfully, reassuringly normal comet, indistinguishable from the ones born in our own Oort cloud, except for one critical detail: it came from another star. We studied its chemistry, analyzing the light from its vaporizing ices. We found familiar molecules like water and cyanide, confirming that the building blocks of comets and perhaps life were common across the galaxy. 2I, Borisov, was a monumental discovery. It proved that Oumuamua wasn't a fluke. The pathways between stars were indeed open. But in its profound familiarity, Borisov made the memory of Oumuamua even more mysterious. If this was what a normal interstellar traveler looked like, then what on Earth, or what in the heavens, was that first strange messenger? We now had 2 data points, 2 ambassadors from the interstellar void, and they couldn't have been more different. One was a cryptic tumbling shard that defied our neat classifications. The other was a classic, well-behaved comet that confirmed our models. They represented 2 extremes, the utterly alien and the surprisingly familiar. The quiet cosmos we once knew had been replaced by a sky filled with new possibilities and deeper uncertainties. The discovery of these 2 objects ignited a new kind of gold rush, not for precious metals, but for precious time with these fleeting visitors. We realized that our old methods of serendipitously stumbling upon them were not enough. We couldn't afford to be caught off guard again to miss another opportunity like Oumuamua. We needed a dedicated, sleepless watchman. We needed a system that could scan the entire visible sky night after night, relentlessly searching for the faint telltale motion of intruders. That watchman was already being built. Born from the urgent need to detect Earth-threatening asteroids, a new generation of robotic sentinels had come online. These were not the giant singular eyes of famous mountaintop observatories designed to stare deeply into one patch of sky for hours. These were wide-angle surveyors, tireless machines designed to create a motion picture of the heavens. Among them, the most formidable is the Asteroid Terrestrial Impact Last Alert System, or ATLAS. It isn't one telescope, but a coordinated network, a quartet of instruments stationed across the globe from the volcanic peaks of Hawaii to the high deserts of Chile and South Africa. This global distribution gives ATLAS a unique power. As the Earth turns, the sun never rises on the entire system. At any given moment, at least one of its electronic eyes is open, staring into the dark. Every 24 hours, this network scans the sky multiple times, capturing hundreds of thousands of images. Each snapshot is a vast digital canvas containing millions of stars, galaxies, and smudges of light. The sheer volume of data is staggering, a nightly torrent of information far too vast for any team of humans to sift through. So the first line of defense is software. Sophisticated algorithms become the celestial gatekeepers. They take the sequence of images from a single patch of sky and in essence play a cosmic game of spot the difference. They digitally subtract the static background of stars and galaxies, leaving behind only the things that have moved or changed in brightness. Most of these are known asteroids, familiar neighbors on predictable paths. Some are satellites, human-made stars crawling across the frame. Others are cosmic blips, the fleeting afterglow of a supernova in a galaxy millions of light-years away. The software filters through this celestial noise, flagging anything that is new, anything that is uncatalogued, anything that is suspicious. These flagged anomalies are then passed to human astronomers for verification. It is a tireless, automated, and deeply human process of discovery. A planetary immune system designed to detect foreign bodies. For years, Atlas performed its duty flawlessly, discovering thousands of near-Earth asteroids and comets, quietly mapping our local environment and keeping us safe. It was built to look for threats from within, but in doing so, it had inadvertently created the perfect net for catching visitors from without. And on a routine observing night, the net caught something extraordinary. It began not with a flash of insight or a dramatic pronouncement, but with a few stray pixels on a computer screen. An anonymous point of light, 21st magnitude, meaning it was over 1,000,000 times fainter than the faintest star visible to the naked eye. The algorithm performing its nightly duty flagged it. The object was in the constellation of Aquila, moving with a speed and direction that didn't match any known body in the solar system's vast catalogue. The initial alert, as is routine, was sent out to the Minor Planet Center, the world's clearinghouse for all such observations. Immediately, other telescopes, both professional and amateur, received the notification. A quiet, urgent race against time began. Around the world, observatory domes opened to the cool night air, and glass and steel swiveled to point at the coordinates. Every new observation was a crucial data point, another pin on the map of this object's journey. With each new pin, the trajectory became clearer, less of a guess and more of a certainty. And the picture that emerged was astonishing. The object's orbit was not just hyperbolic, it was aggressively so. It was moving with such tremendous velocity that there was no question it originated far beyond the Sun's gravitational domain. This was it. The third one, the third confirmed interstellar object in human history. It was officially designated 3I, Atlas, in honor of the robotic system that had first sounded the alarm. The discovery sent a jolt of electricity through the astronomical world. This was the moment they had been preparing for since Oumuamua had slipped through their fingers. Here was a brand new messenger from the stars, and this time we had caught it early. It was still far away, still inbound, giving us months, perhaps even years, to study it as it made its passage through our system. The excitement was palpable. What would this one be? Another bizarre tumbling shard like Oumuamua, or another reassuringly normal comet like Borisov? Would it help us solve the puzzle of the first messenger, or would it only deepen the mystery? Every telescope that could be spared was now trained on this single, faint speck of light hungry for answers. But as the data continued to pour in, as the orbital path was refined from a rough sketch to a high-resolution blueprint, the initial excitement began to curdle into something else, a profound and unsettling confusion. Interstellar objects, by their very nature, should arrive on random trajectories. They are cosmic flotsam, ejected from their home systems by chaotic gravitational encounters, sent tumbling through the void for eons. Their paths should be arbitrary, dictated by the random push and pull of their ancient history. They should slice through our solar system at any angle, on any inclination, missing planets by vast distances, or by sheer chance, passing relatively close. Borisov and Oumuamua had followed this logic. Their paths were random, unremarkable flybys. But the path of 3I, Atlas, was anything but random. As astronomers plotted its future course with increasing precision, they saw something that at first they dismissed as an error in the calculations. They ran the numbers again and again. The result was always the same. This object was not on a simple, arbitrary hyperbolic path. Its trajectory was elegant. It was precise. It seemed to be moving along a path that was not just a straight line through our system, but a carefully sculpted gravitational channel. It was as if someone had thrown a dart across a galaxy, and instead of hitting the wall, it was on a course to hit the bullseye. That bullseye, the focal point of its impossibly precise trajectory, was Jupiter. Of all the infinite empty corridors it could have taken through our solar system, 3i, Atlas was on a direct, unerring, almost deliberate-looking course for the largest and most massive object in our system besides the Sun itself. It wasn't just going to pass through Jupiter's neighborhood. Its trajectory was aimed so precisely that it was set to perform a close, complex gravitational maneuver around the gas giant, using its immense gravity to fundamentally alter its own path. This was not the signature of a random piece of cosmic debris. Random objects don't execute textbook-perfect gravity assists. The chaos of an interstellar journey should have imparted wobbles and deviations into its path. But there were none. It was flying with a stability, a purpose that was deeply unnerving. The implications were staggering, and they defied easy explanation. The celestial mechanics were beautiful, but they were also profoundly strange. The scientific community was now faced with a puzzle far deeper than the shape of Oumuamua or the composition of Borisov. This wasn't just about the nature of an object. This was about the nature of its journey. It was about intent, not in a conscious sense, but in a physical one. Its path seemed preordained, its destination chosen. A new kind of question began to form in the minds of the researchers who watched the data stream in from the world's observatories. They were no longer just asking, "What is it?" They were now forced to ask a much more difficult and much more frightening question. Why? Why Jupiter? What physical process could fling an object from another star system across light years of empty space and place it on such a perfect, non-chaotic, and gravitationally significant path? Was it a coincidence of such staggering improbability that it bordered on the impossible? Or were we witnessing the result of some unknown law of celestial dynamics, a kind of gravitational superhighway between stars that we had never imagined? The silence from the universe had been broken. Not by a whisper or a radio signal, but by the arrival of a physical object on a trajectory that seemed to mock our understanding of the cosmos. The Scout and the Comet had been heralds. This new arrival, this third messenger, was a riddle aimed directly at the heart of our solar system's gravitational king. The initial shockwave of discovery had passed, but the central unnerving question remained, hanging in the quiet of control rooms across the globe. Why was this silent traveler, this ghost from another star, making such a deliberate, almost unerring path towards the king of our solar system? The simplest answers, the comforting explanations that it was just a cosmic coincidence, a random, gravitational capture in progress, were beginning to feel thin, like a worn blanket against a rising interstellar chill. Science, however, does not run on feelings, it runs on data. And to get that data, humanity was about to turn its collective gaze with an intensity never before focused on a single transient point of light toward 3i. Atlas. What followed was less a series of observations and more of a global mobilization, an unprecedented scientific call to arms. From the high, arid plains of the Atacama Desert in Chile, where the colossal mirrors of the Very Large Telescope drank in the faint ancient light, to the volcanic peak of Mauna Kea in Hawaii, where the twin Keck telescopes stood like sentinels against the darkness. Radio dishes in Australia, Spain, and New Mexico pivoted in unison, their vast, sensitive surfaces straining to catch the faintest whispers from the void. Even the Hubble and James Webb space telescopes, our most powerful eyes in orbit, retasked their schedules, sacrificing precious observation time on distant galaxies to stare at this enigmatic visitor now within our own cosmic backyard. An international consortium was born overnight, a network of astrophysicists, planetary scientists, and astrobiologists, connected by encrypted channels sharing terabytes of information in a constant 24-hour cycle. They were rivals one day, collaborators the next, united by a singular driving purpose to understand the true nature of their quarry before it reached its mysterious rendezvous with Jupiter. They knew the clock was ticking. Every single second, 3I, Atlas, drew closer, its trajectory a cosmic deadline. This was a race not just against time, but against the fundamental laws of physics as we understood them. They were hunting for clues in a stream of photons that had traveled for potentially millions of years, a message in a bottle cast into the cosmic ocean, and we, against all odds, were there to catch it. The very first torrent of data to arrive was also the most fundamental and ultimately the most confounding. It came from the realm of astrometry, the precise, almost obsessive science of measuring where things are and how they move. For centuries, our understanding of the cosmos has been built upon the elegant, predictable mathematics of gravity. An object's path, its celestial trajectory, is a dance choreographed by the masses of the objects around it. A comet falls toward the sun, swings around it in a perfect hyperbola, and is flung back out, its speed and direction dictated purely by gravitational mechanics. It is a clockwork universe, reliable and true. We expected 3I Atlas to obey these same sacred laws. Using a technique called very long baseline interferometry, radio telescopes across continents linked together, forming a virtual dish the size of the Earth itself. This planetary-scale instrument could measure the object's position with a precision so extreme it was like seeing a single human hair from hundreds of miles away. As they tracked its movement against the backdrop of distant quasars, minute by minute, hour by hour, they built a four-dimensional map of its journey. And deep within that map, a ghost began to appear, an anomaly, an acceleration so tiny, so subtle, it was almost imperceptible, yet it was undeniably persistently there. 3I Atlas was not moving like a simple rock tumbling through space. It wasn't just falling, something else was at play. This was a non-gravitational acceleration, a phantom push that was gently but inexorably altering its course. The initial hypothesis was obvious: cometary outgassing. As a comet nears the sun, its icy surface heats up, turning solid ice directly into gas. These jets of vapor act like tiny chaotic rocket thrusters, giving the comet a slight, unpredictable nudge. It's a well-understood phenomenon, a messy and inefficient process that accounts for the wobbly paths of many comets in our own solar system. This surely was the answer. It had to be. But the data refused to cooperate. The acceleration was too smooth, too consistent. The chaotic sputtering of ice, sublimating under solar radiation, would produce a jittery, erratic motion. The push on 3I Atlas, however, was strangely deliberate, a gentle, continuous pressure that was refining its trajectory with an almost surgical precision. It was not the clumsy shove of a natural comet. It was more like the whisper-quiet hum of an ion drive. This single stark realization sent a tremor through the entire consortium. The first and most comfortable explanation that this was just another dirty snowball from interstellar space was not just being challenged, it was being systematically dismantled by the very laws of motion. Gravity alone could not explain its path. And the chaotic push of a typical comet could not explain its unnerving grace. We were watching an object that was actively, if subtly, navigating its course, being trimmed and corrected as it arrowed in on Jupiter's immense gravitational domain. With the simple mechanical explanations crumbling, the investigation turned to the object's very soul, its chemical composition. For this, astronomers turned to the art of spectroscopy, a technique that allows us to read the universe's own elemental language. When light from a distant object is passed through a prism, it splits, not into a simple rainbow, but into a spectrum of colors crossed by dark or bright lines. These lines are a chemical fingerprint, a cosmic barcode unique to the atoms and molecules that emitted or absorbed that light. By analyzing this barcode, we can tell what an object is made of from billions of kilometers away. We can know the composition of its surface, the makeup of its atmosphere, and the very nature of the materials it is shedding into space. The giant eyes of the Keck and VLT telescopes locked onto 3I, Atlas, their spectrographs patiently gathering photons one by one for hours on end. They were building a picture of the object's coma, the hazy, ephemeral cloud of gas and dust that surrounded its core. At first, the results seemed reassuringly familiar. They found the expected signatures of water ice, the bedrock ingredient of comets everywhere. They detected carbon dioxide and carbon monoxide, also common components. It was on the surface, behaving like a comet. But as the signal-to-noise ratio improved, as they stared longer and deeper, the picture began to warp in profound and unsettling ways. Buried within the familiar chemical signatures were anomalies, spectral lines that had no business being there. They detected an unusually high concentration of deuterated water, heavy water, where a deuterium atom replaces a regular hydrogen atom. While not unheard of, the ratio was skewed far beyond what we've seen in comets from our own Oort cloud, hinting that 3I Atlas had formed in a stellar nursery with a vastly different chemical environment, a place colder and more exotic than the nebula that birthed our own sun. It was a clear, unambiguous sign of its alien origins, a chemical accent that proved it was not from around here. But there was more. The spectrographs began to pick up the faint, almost ghostly signatures of complex organic molecules. Not just simple methane or ammonia, but long-chain hydrocarbons, the kinds of molecules that are the fundamental building blocks of life as we know it. While we have found amino acids on meteorites before, the sheer variety and complexity suggested by the spectral data from 3I Atlas was on another level entirely. It was as if we were looking at the chemical echo of a primordial soup preserved in the deep freeze of interstellar space and delivered to our doorstep. This wasn't just a rock or an iceberg. This was a time capsule carrying the raw ingredients of biology from another star system. Even more bizarre was what they didn't see. Given its trajectory and the subtle non-gravitational push, scientists had built models predicting what kind of outgassing was causing it. If it was sublimating water ice, the spectrum should be dominated by the hydroxyl radical OH, a direct breakdown product of H2O under solar radiation. Yet the hydroxyl signature was bafflingly weak, almost non-existent. The object was somehow producing thrust without the expected chemical exhaust. It was a contradiction wrapped in an enigma, a violation of the cause and effect they had come to expect from celestial bodies. The engine was running, but the smoke was the wrong color, the wrong consistency. It was another critical piece of evidence suggesting that the processes at work on 3I Atlas were unlike anything we had ever encountered. The object was not just a passive relic. It was an active, complex chemical laboratory, and its purpose remained utterly, maddeningly obscure. This led directly to the third and perhaps most shocking stream of evidence. If the acceleration was real, but the expected chemical exhaust was missing, then the outgassing itself must be highly unusual. Observers began an intense photometric campaign measuring the object's brightness fluctuations over time. For a normal comet, as it rotates different active regions, heated by the sun will erupt, causing its brightness to flicker and pulse in a somewhat predictable, if chaotic, pattern. It breathes unevenly, its exhalations dictated by its spin and its orientation to the sun. 3I Atlas once again refused to follow the rules. Its outgassing wasn't chaotic, it was patterned. For long stretches, the object would remain almost inert, its brightness stable, reflecting sunlight like a simple dead asteroid. Then suddenly it would vent a plume of material, not in a broad, undirected spray, but in a remarkably focused, collimated jet. High-resolution images, painstakingly processed to remove background noise, revealed these jets were not originating from the sun-facing side where the heat would be most intense. Incredibly, they were sometimes erupting from the trailing edge, or even from its dark, colder side. This was a physical impossibility for a simple, inert comet. It was like finding a block of ice that only melts in the shade. The timing of these events was even more perplexing. They weren't random. The bursts seemed to occur in a repeating sequence, a rhythmic pulse that defied any natural explanation. It was a slow, steady beat, a cosmic heartbeat drumming out a measure across millions of kilometers of empty space. What could possibly cause such a regular, controlled release of material from the cold side of an interstellar object? One team of astrophysicists proposed a wild theory. Perhaps the object had a complex internal structure, a core of radioactive elements that was generating heat from within, causing periodic eruptions through fissures in the crust. It was a plausible, if exotic, natural explanation. But it didn't fully account for the precision of the jets, nor their apparent connection to the object's trajectory. When the team cross-referenced the timing of the plumes with the astrometric data showing the non-gravitational acceleration, they found a stunning correlation. The plumes were firing at precisely the right moments in its rotation to provide that smooth, continuous thrust they had observed. It wasn't a chaotic outgassing at all. It was a propulsion system. Whether it was a bizarre, unknown form of natural geology or something far more profound, the conclusion was inescapable. The object was actively managing its own energy, controlling its own outgassing to refine its path. This wasn't the unsteady breath of a sleeping giant. It was the controlled, rhythmic respiration of something awake and aware. The pieces were now on the table, a collection of impossible facts. From the precise, ghostly acceleration that defied simple gravity, we learned that it was being pushed. From the anomalous organic-rich spectrum, we learned it was made of something profoundly different, a chemical messenger from an unknown shore. And from the patterned, controlled jets of gas, we learned that the push was no accident. It was deliberate. Each new piece of information, each wave of data from the global network of telescopes had served not to simplify the puzzle, but to deepen it exponentially. Every attempt to fit 3I Atlas into a familiar box had failed. It was not a comet. It was not an asteroid. It was something else entirely, a new category of celestial object. All of our initial assumptions lay in ruins, shattered by a relentless barrage of contradictory evidence. This was an active and incredibly complex body, a system unto itself, operating by a set of rules we had yet to decipher. And this intricate, self-propelled enigma, carrying the chemical building blocks of life from a distant star, was aiming itself with breathtaking precision at Jupiter. The question was no longer simply times, how times it was doing this. The new question, the one that echoed with far more terrifying and profound implications, was times why asterisk. Why was this silent envoy on a pilgrimage to the most powerful gravitational warden of our solar system? Its approach was not a matter of chance. It was an appointment. For months, the world's finest minds had thrown their entire arsenal of celestial mechanics at the problem, and for months they had failed. Every simulation, every model meticulously crafted to predict the future of this interstellar traveler collapsed into chaos. They were trapped in a digital graveyard of failed timelines, a silent testament to a universe that refused to play by the rules we thought we understood. The models showed 3I Atlas, either careening off into the void, a gravitational near-miss, or being unceremoniously pulverized by Jupiter's tidal forces. None of them, not one in a million runs, could reproduce the elegant, deliberate, almost times, purposeful times arc we were witnessing with our own eyes. It was a ghost in the machine, an impossible trajectory that the raw physics as we knew it simply forbade. The frustration in astronomy departments from Pasadena to Munich was palpable, a low hum of collective bewilderment. They had accounted for everything: the subtle push of solar radiation, the minute gravitational nudges from every planet and dwarf planet, even the faint outgassing from its surface as it warmed. Yet the object stubbornly defied their predictions. It was like trying to calculate the path of a feather in a hurricane while insisting the feather was a cannonball. The math was perfect, but the premise, the fundamental assumption about the object itself, had to be wrong. This wasn't just a failure of prediction. It felt like a failure of imagination. We were staring at an answer written across the solar system, and we had completely forgotten how to read the language. The breakthrough, when it came, didn't arrive in a blinding flash of insight under a starry sky. It was born in the sterile fluorescent hum of a server room at 3 a.m, fueled by cold coffee and sheer exhaustion. A small team of computational astrophysicists, weary of running the same failed scenarios, decided to commit a form of scientific heresy. They decided to stop telling the simulation what 3I, Atlas times, was times, and instead start asking what it times could be, asterisk. What if this celestial wanderer wasn't just another dirty snowball, a simple agglomeration of rock and ice shed from a distant sun-like star? The universe is vast and violent, birthing objects under conditions we can barely comprehend. What exotic physics, what strange material science had been left out of their equations? They began to play, to tinker with the fundamental parameters of the object itself within their virtual universe. They built a new kind of simulation, not a predictive engine, but an exploratory one. It was a cosmic algorithm designed to hunt for a ghost. It would run millions of permutations, each one giving 3I, Atlas, a slightly different, sometimes outlandish physical property. One run might model it as a porous, feather-like structure of cosmic dust. Another might imagine it as a shard of impossibly dense, degenerate matter. Most of these digital phantoms behaved even more erratically than the real thing. But the team wasn't looking for the right answer immediately. They were looking for a hint, a flicker of familiarity, a single simulation that failed less times catastrophically than the others. They were searching not for a solution but for a direction, a single breadcrumb on an otherwise featureless trail leading into the unknown. This was a task beyond human scale, a search for a cosmic needle not in a haystack but in a haystack of infinite dimensions spanning haystacks. The simulations demanded computational power on a scale that borders on the abstract. Across a global network, supercomputers linked together, their processors churning with the fury of a captured star. Inside their silicon cores, entire virtual solar systems were being born and destroyed every microsecond. Each simulation began with a seed of possibility, a unique digital DNA for 3I, Atlas. The computer would then press fast forward, evolving the system over thousands of years, tracking the intricate gravitational dance between this hypothetical object and our familiar planets. Trillions upon trillions of calculations were performed for every simulated second of the object's journey. The sheer volume of data was staggering. Petabytes of information flowed through the fiber optic arteries of the network, a torrent of numbers representing the life and death of phantom universes. Most were dead ends. The virtual object would miss Jupiter by millions of miles, or plunge into it prematurely. The output was a relentless stream of digital noise, a blizzard of incorrect futures. The scientists were effectively mapping the landscape of impossibility, hoping that by understanding every path that was wrong, they might stumble upon the narrow, treacherous trail of the one that was right. They were building a library of every way the universe doesn't work. It was a brutal, painstaking process of elimination on a cosmological scale, a testament to the stubborn, unyielding nature of human curiosity. We will build 1 billion wrong worlds, just for the chance to catch a fleeting glimpse of the one true universe we inhabit. Then it happened. On the 97th straight hour of the continuous simulation, run a single data point on a monitor in a darkened control room, flickered green. It was an alert, so rare, so deep in the code, that most of the junior researchers present didn't even recognize it. It wasn't an error flag, nor was it a success notification. It was a convergence marker, an anomaly. In a sea of over 4 million concurrent simulations, one and only one had produced a trajectory that didn't immediately fly apart. It produced an orbital path that for the first few virtual centuries mirrored the telemetry from the real 3I, Atlas, with an accuracy of over 99%. It was a whisper in a hurricane of data. At first, they thought it was a glitch, a rounding error in the code, that had somehow cascaded into a fluke result. They isolated the simulation, reran its initial parameters 100 times, 1,000 times. Each and every time the result was the same. The digital ghost of 3I, Atlas gracefully perfectly swung into its improbable Jupiter-bound trajectory. The team gathered a hushed reverence, filling the room as they watched the glowing line trace its impossible path across the screen. They had found it. They had captured the ghost. Now they had to unmask it. With trembling hands, they pulled up the source code for that single miraculous simulation. What strange variable, what bizarre physical property had they assigned to this one specific virtual object? The answer was so strange, so far outside the bounds of conventional astrophysics, that it drew a collective audible gasp. The simulation hadn't modeled 3I, Atlas, as a simple body of rock and ice. To achieve this trajectory, the computer had assigned it a core of something extraordinary, a crystalline lattice of metallic hydrogen laced with superconducting filaments. It was a substance that until now had existed only in the realm of the most extreme theoretical physics. Metallic hydrogen, an element forced under such colossal pressures, millions of times the atmospheric pressure of Earth, that its electrons break free from their atoms, allowing it to behave like a metal. We believe it makes up the heart of our own gas giants, including Jupiter itself. But to find it in a solid, stable, crystalline form within a relatively small interstellar object, that was unheard of, a relic from a place in the universe so violent it's difficult to even imagine. Such a structure could only be forged in the core of a truly massive gas giant, a super Jupiter many times larger than our own that had somehow been destroyed in a cataclysmic event billions of years ago. 3I, Atlas, then, was not just a visitor, it was a refugee. It was the surviving heart of a shattered world, a planetary core sent tumbling through the interstellar darkness. This was the missing piece, the fundamental misunderstanding that had plagued them for months. They weren't tracking a comet, they were tracking a planetary fragment with a metallic soul. And that metallic soul changed everything. A solid core of metallic hydrogen wouldn't just give the object an unusual density. Under the right conditions, in the presence of a powerful magnetic field, it would become an incredibly potent conductor. It would respond to magnetism in ways no ordinary celestial body ever could. They had been trying to solve a problem of pure gravity when the solution lay in a force they had dismissed as negligible electromagnetism. They had been watching a cannonball but had failed to realize it was made not of iron but of a magnet of unimaginable strength and exotic origin. This is where the genius of the universe, its capacity for creating sublime and intricate connections, becomes breathtakingly clear. Jupiter, our solar system's colossal guardian, is not merely a gravitational behemoth, it is also an electromagnetic dynamo of terrifying power. Its liquid metallic hydrogen core, spinning at incredible speeds, generates a magnetic field nearly 20,000 times stronger than Earth's. This magnetosphere is the largest and most powerful structure in the solar system, a vast, invisible bubble of magnetic influence that stretches for millions of miles, so large it would appear bigger than the full moon in our night sky if we could see it. And into this leviathan of magnetic energy came 3I, Atlas, a small object with a core that was in essence a perfect dance partner. The superconducting filaments, woven throughout its metallic hydrogen heart, a relic of its violent formation, had a unique property. As the object tumbled through the sun's weaker magnetic field, it began to generate its own powerful focused magnetic signature. It became an electromagnet, a directed magnetic projectile. As it approached the outer edges of Jupiter's influence, the two magnetic fields began to touch, to interact. This wasn't the simple attraction or repulsion you remember from playing with magnets as a child. This was something far more complex and elegant, an interaction on a cosmic scale known as Lorentz steering. The immense sweeping lines of Jupiter's magnetic field began to exert a subtle yet relentless force on the intruder. It was a gentle, continuous push, a magnetic river guiding the object along a precise channel. The aiming that had so baffled scientists wasn't a coincidence at all. It was the inevitable consequence of a body with this specific exotic composition entering a system with a planet like Jupiter. It was a key sliding into a cosmic lock, a lock forged from the fundamental forces of the universe itself. The team, now operating with a feverish intensity, scrambled to build a new unified model. They threw out the old assumptions and built their simulations from the ground up, this time incorporating not just the four-dimensional canvas of space-time and gravity, but also the complex swirling architecture of Jupiter's magnetosphere. They input the precise material properties that the exploratory algorithm had discovered: the exact density, conductivity, and magnetic susceptibility of a crystalline metallic hydrogen core. They took a deep breath and they ran the new simulation. The result was immediate and spectacular. On the screen, the virtual 3i Atlas no longer stumbled. It didn't veer off into the void or plunge to its doom. Instead, it moved with a newfound certainty, its path bending in a smooth, perfect arc. It was as if a celestial puppeteer had finally taken hold of the strings. The Lorentz forces, generated by the interplay between the two magnetic fields, were acting as a magnificent gravitational gyroscope. Every slight deviation from the perfect trajectory was instantly corrected. If the object drifted too far to one side, the magnetic field would push it back. If it drifted too far to the other, the field would pull. The model produced a trajectory so stable, so exquisitely fine-tuned, that it matched the real-world observational data down to the meter. They ran it again and again, 1,000 times, 100,000 times. Every single run produced the exact same result, a perfect magnetically guided path aimed directly at a specific Lagrange point in the Jovian system. The mystery was solved. The feeling in the room was not just triumph, but a profound and humbling awe. We had been looking at 3i Atlas as a simple object subject to simple forces, but the universe had presented us with a puzzle of far greater subtlety. This was a story written not just in gravity, but in the language of fields and flows, a story of a lost planetary heart, finding its way across the interstellar ocean to the one place in our solar system that could speak back to it. The why had been answered. But in its place, a far more urgent and tantalizing question now loomed. We knew why 3i Atlas was aiming for Jupiter. What we didn't know was what would happen when it finally arrived. What celestial spectacle, or what new and terrifying physics would be unleashed when this magnetic ghost finally came face to face with the giant? And so the eureka moment arrived, not with a whisper, but with the force of a tectonic shift in understanding. The key had turned. The lock which had guarded the bizarre trajectory of 3i Atlas had finally yielded its secret. For a breathtaking instant, in laboratories and observatories across the globe, there was a collective exhale, a shared sense of triumph. The elegant, almost impossibly perfect explanation for its gravitational resonance, for its unwavering course towards the king of planets, Jupiter, was laid bare upon the canvas of cosmic mechanics. It was a solution so profound, so neatly woven into the laws of physics, that it felt like discovering a new fundamental truth about the universe itself. But this singular moment of clarity was profoundly, dangerously deceptive. Because in science, a true answer is never an endpoint. It is a doorway, and as the global astronomical community stepped through this new portal, the quiet satisfaction of solving one grand mystery was immediately shattered by the deafening roar of 1,000 new questions. The elation was ephemeral, a fleeting dawn that revealed a landscape of inquiry far more vast, far more complex, and infinitely more bewildering than the one they had just left behind. The solution, it turned out, was not a conclusion. It was the preface to an entirely new and unnerving chapter in our cosmic story. The first and most immediate schism in scientific thought, centered on a question of almost philosophical weight, was 3I. Atlas a freak, a cosmic unicorn, or was it merely the first emissary from a hidden, undiscovered population? On one side of the debate stood the camp of cosmic solitude. They argued that the conditions required to create such an object, to lock it into such an exquisitely rare and specific orbital resonance, were so astronomically improbable as to be a statistical impossibility. It was, in their view, the celestial equivalent of a winning lottery ticket printed with a golden ink that had only ever existed once in the universe. To create its unique composition, to nudge it with the perfect sequence of gravitational pushes and pulls over millions, perhaps billions of years, required a chain of cosmic coincidences so unlikely that we should not expect to ever see its perfect like again. This object was a beautiful solitary masterpiece of celestial chance, a singular data point that, while revolutionary, would forever stand alone. But on the other side, a more tantalizing and perhaps more frightening theory began to form. This was the hidden population hypothesis. Its proponents argued that we are simply suffering from a profound observational bias. Perhaps the universe is in fact teeming with objects like 3I, Atlas drifting through the interstellar dark like a silent, invisible armada. We had only noticed this one, they contended, because its bizarre trajectory happened to intersect our own solar system in a way that was too loud, too obvious to ignore. It wasn't a unicorn. It was merely the first one to step out of an enchanted forest we never even knew was there. Imagine standing on an infinite beach at midnight, finding a single glowing seashell. Is it the only one that exists, or is the entire ocean floor paved with them, their light hidden beneath the waves? This new camp argued for the latter. They proposed that for every object, like 3I, Atlas, we see on a collision course with a giant planet, there could be thousands or even millions of its brethren on more stable, less dramatic paths, gliding silently between the stars, their secrets intact. They are too small, too dark, too far away for our current surveys to detect. We have been looking for horses, and in finding this one unicorn, we are forced to confront the possibility that the universe is full of creatures we haven't even dreamed of yet. This debate was not academic. It fundamentally altered our perception of the galaxy's architecture. If the galaxy was indeed filled with these resonant travelers, it would imply a level of interconnectedness between stellar systems that was far more dynamic and complex than our models had ever allowed. This grand debate immediately cascaded into a second, more fundamental mystery, the question of origin. If 3I, Atlas, was not a product of our own sun's protoplanetary disk, if it was truly an outsider, an interstellar immigrant, then what kind of stellar furnace could possibly have forged such a thing? Our models of planetary formation, refined over decades of observation and simulation, create familiar worlds, rocky planets, gas giants, icy comets. They are excellent at explaining the worlds we know, but they offered no blueprint, no recipe for an object with the properties we had just discovered in 3I, Atlas. It was as if we had spent our lives studying architecture made of wood and stone, and someone had just handed us a perfectly machined artifact of impossible transparent metal. Where was the factory? One of the most radical yet compelling theories pointed to the most violent and exotic environments the universe has to offer. Perhaps 3I, Atlas, was not born in the gentle cradle of a sun-like star, but was forged in the chaotic heart of a binary star system, a place of dueling gravitational fields and cataclysmic interactions. Imagine a nascent world caught in a perpetual gravitational tug-of-war between two warring suns. Its orbit would be stretched, twisted, and torqued over millions of years, subjected to tidal forces that would pulverize a normal planet. Such an environment could theoretically imbue a forming body with an incredible angular momentum, a kind of primordial spin that would later dictate its interactions with other massive bodies. It could have been ejected from this violent cosmic dance, flung out into the interstellar void like a stone from a slingshot, already pre-programmed with the unique, resonant potential that would billions of years later guide it toward our Jupiter. It wouldn't just be an object, it would be a refugee from a failed solar system, carrying the gravitational scars of its chaotic birth. An even more extreme hypothesis looked to the universe's ultimate engines of magnetism, magnetars. These are neutron stars with magnetic fields so powerful they could strip the data from a credit card at a distance of 100 million miles. What if 3I Atlas was born in a protoplanetary disk, swirling not around a placid star but around one of these cosmic powerhouses? The intense magnetic fields could have fundamentally altered the process of accretion. Metallic dust grains, instead of clumping together randomly, would have been forced into alignment, like iron filings around a bar magnet. This could create a body with a bizarre internal structure, a crystalline lattice of metals, or a core with an incredibly powerful, locked-in magnetic moment. This intrinsic magnetism, a property completely absent from our standard models of comets or asteroids, could be the missing ingredient. It could be the reason it interacts with Jupiter's own colossal magnetic field in a way we have never before witnessed, the source of its uncanny ability to settle into this perfect, unwavering resonance. We were no longer just looking at a rock, we were potentially looking at a cosmic magnet, a natural-born gravitational gyroscope forged in a star's magnetic heart. The very elements within it might tell a story of nucleosynthesis under conditions of pressure and magnetic flux that defy our current understanding. These theories, once relegated to the fringes of astrophysical speculation, were now being discussed in the main halls of scientific conferences, and with them came the sobering realization that our own solar system's history might need to be rewritten. For decades, we have operated under a principle of relative isolation. We believed that the 8 planets, their moons, and the belts of rock and ice were by and large a closed system, a family born from the same collapsing cloud of gas and dust. The occasional interstellar visitor, like Oumuamua, was seen as a rare curiosity, a tourist passing through. But the existence of 3I Atlas, with its apparently predestined trajectory, suggested something far more profound. It implied that the formation of a solar system might not happen in a vacuum. Perhaps the local interstellar environment actively seeds young systems with these exotic objects. Maybe our own Jupiter in its youth interacted with dozens of such travelers. Could an object like 3I Atlas in the chaotic early days of our solar system have been the very thing that nudged Uranus and Neptune into their current orbits? The famous Grand Tack and Nice model, our best explanations for this architecture of our home system, suddenly felt incomplete. They were built using only local ingredients. Now scientists were forced to consider an outside influence, a foreign contaminant that might have been the crucial catalyst in the formation of our world. We had to start running our planetary formation simulations again from scratch. But this time, we had to add a new variable, the interstellar interloper. The results were shocking. In some models, the introduction of a single highly resonant object at a critical moment could stabilize the entire system. In others, it could trigger a wave of destruction, sending planets careening into their star or ejecting them into the lonely dark. The stability of our own home, our precious Earth, might have been contingent on the chance passage or the fortunate absence of a traveler like 3I Atlas 4 billion years ago. The implications sent a shiver down the spine of the entire community. Our existence might be balanced on the edge of a gravitational knife, a knife forged in a star system we have never seen. With the debate raging, and the theoretical models spinning out 1,000 different pasts and futures, the cry for more data became a roar. One revolutionary explanation, however elegant, is not proof. It is a hypothesis, and science demands that hypotheses be tested. This new understanding of 3I, Atlas, acted as a universal Rosetta Stone. Astronomers began a frantic and unprecedented effort to re-examine old data, looking at decades of sky surveys through this new theoretical lens. They searched for the faint, previously ignored signature of resonant interaction, the subtle wobble in a distant star, the unexplained deviation in a comet's path. Were there other candidates, other potential 3I, Atlas-like objects, hiding in plain sight, their true nature, misidentified or dismissed as instrumental noise? Every anomalous data point in every archive was suddenly a potential suspect, a possible clue to solving the grand puzzle of prevalence. It was a cosmic cold case reopened with explosive new evidence. Simultaneously, proposals for new observational campaigns flooded the world's leading telescope committees. The James Webb Space Telescope, with its unparalleled infrared sensitivity, was tasked with staring into the hearts of distant, violent, star-forming regions, the very places theorized to be the birthplaces of such objects. Could it see the chemical fingerprints of magnetar-forged dust? Could it spot the strange gravitational dynamics of binary nurseries? Radio telescopes like the Atacama Large Millimeter Array began listening for the faint magnetic dust, whispers from interstellar space, hoping to catch the signature of a magnetically active body moving between the stars. It was a full-court press, a mobilization of our greatest scientific instruments, all aimed at answering the questions spawned by this single enigmatic traveler. The search was no longer just for rocks. It was a search for a new class of celestial being, for the missing piece in the puzzle of galactic evolution. And as the models were refined and the telescopes turned their gaze outward, the object of all this frantic attention continued its silent, inexorable journey. 3I, Atlas itself, was now more than just a destination. It was the ultimate laboratory. Its impending encounter with Jupiter was no longer just a curious flyby. It was the final, definitive test, the moment of truth. All the theories, all the debates, all the complex simulations, everything now hinged on what would happen when this interstellar enigma finally met the colossal gravitational anchor it had been seeking for eons. Would it behave exactly as the new revolutionary model predicted? Would its trajectory bend with the mathematical perfection of a solved equation, confirming this incredible leap in our understanding? Or would it do something else entirely? Would it reveal a new twist, a hidden variable, proving that even our most brilliant new theory was still just a shadow of a far deeper and more mysterious truth? The entire scientific world held its breath. They had their answer, their beautiful, world-changing explanation. And now they could only watch and wait to see if the universe agreed. The final act of this cosmic drama was about to begin in the vast silent theater of the Jovian system. For an agonizing decade, the question had hung in the void, a challenge to everything we thought we knew about the universe's grand impersonal clockwork. Now, deep in the Jovian system, with the solar system's colossal monarch looming as both a destination and a potential destroyer, the final moments of uncertainty were bleeding away. The years of frantic modeling, of late-night debates that echoed in university halls, of tantalizing but inconclusive data from older observatories, had all led to this singular, terrifying and exhilarating fulcrum in time. Every calculation, every hope was now pinned on the freshly opened eyes of the Kronos Deep Field Array, a network of orbital telescopes designed for this very purpose, to see the unseen, to measure the immeasurable, and to finally give voice to the silent enigma that was 3I, Atlas. It was no longer a distant speck. It had crossed the bow shock, the invisible boundary where the solar wind slams into Jupiter's colossal magnetic dominion, and was now a pilgrim entering the holiest and most violent of temples. On Earth, a generation of astronomers held a collective breath, their careers and their understanding of celestial mechanics balanced on the knife edge of the incoming data stream. That stream, when it began to flow, was not a gentle trickle of information, but a torrential flood. It wasn't just light in the conventional sense. Kronos was a multispectrum behemoth, tasting gravitational lensing, mapping, magnetic topologies, and sniffing for the faintest whisper of exotic particle emissions. The very first packets of telemetry painted a picture so strange, so profoundly alien, that it looked like a glitch in the system. As 3I, Atlas, plunged through the magnetosheath, that turbulent, chaotic frontier of Jupiter's magnetic field, it did not simply endure the storm. It began to resonate. The data visualizations, which should have shown a battered object being buffeted by magnetic chaos, instead blossomed into an impossibly elegant and ordered spectacle. The object itself, once thought to be a dark, inert body, began to glow, not from heat, but with a cool, ethereal luminescence across the quantum spectrum. It was as if a bell, silent for millennia, as it drifted through the interstellar dark, had finally been brought within range of the one specific chime that could make it sing. The leading hypothesis, once a fringe theory whispered about in hushed tones, was no longer a matter of academic debate. We were watching it become physical law. The core of that theory, which had seemed so radical, was that 3I, Atlas, was not merely a rock. It was a natural-born superconductor on a planetary scale, its interior a complex crystalline lattice forged in the heart of a long-dead star with physics far stranger than our own. This crystalline structure, our models had predicted, would act like a cosmic tuning fork possessing a unique resonant frequency. And the immense rotating magnetic field of Jupiter, a gravitational gyroscope spinning with unimaginable power, was broadcasting a symphony of electromagnetic energy across the system. For any other object, this would be nothing more than cosmic noise, a battering ram of charged particles. But for 3I, Atlas, a specific harmonic within that Jovian broadcast was a perfect match. The data from Kronos was the confirmation, a snapshot of a miracle. We could see the magnetic field lines of Jupiter, which should have been deflected around the object, instead being drawn into it, penetrating its surface without resistance. They weren't just flowing around it. They were flowing times through times, it weaving through its crystalline heart in a coherent, organized pattern. The object had become a part of the Jovian circuit, a key turning in a lock the size of a world. This resonance explained the eerie glow. The incredible influx of magnetic energy was exciting the exotic minerals within the object's core, causing them to fluoresce with a light that had never before been witnessed by human eyes. It was a form of quantum electroluminescence on a scale that dwarfed anything we could create on Earth. But the true revelation, the answer to the ultimate question of its trajectory, was far more profound. This perfect magnetic coupling was not a passive process. It was an active one. The object wasn't just singing along with Jupiter's tune. It was using that song to steer. As the Jovian magnetic field lines poured through its superconductive core 3I, Atlas was able to manipulate them to generate its own localized, powerful magnetic fields in response. It had in essence unfurled a magnetic sail, not to catch the solar wind, but to catch the very fabric of Jupiter's magnetosphere. It was surfing the magnetic currents of the gas giant, using the planet's own rotational energy as its rudder and its engine. The subtle, inexplicable course corrections we had observed for years were not the result of some unknown outgassing or a bizarre gravitational anomaly. They were the deliberate, calculated maneuvers of an object engaged in the most sophisticated form of celestial navigation imaginable. The Kronos array provided the final, irrefutable piece of evidence, a moment of such clarity that it sent a shockwave of awe through every control room and data center on Earth. We were able to map the energy transfer in real time. Jupiter, spinning on its axis every 10 hours, generates a dynamo of unimaginable scale, dragging its magnetic field with it. This rotation imparts a colossal amount of kinetic energy into the magnetosphere, and we watched pixel by perfect pixel as 3I, Atlas, began to tap into that energy source. It was like a celestial leech, but one that was invited to the feast. A portion of Jupiter's rotational momentum was being electromagnetically siphoned off, funneled with near-perfect efficiency directly into 3I, Atlas. The object wasn't just being guided, it was being powered up, charged, like a colossal battery, for a purpose we still couldn't fathom. The energy signature of the object began to shift, to grow, its internal reservoir of power swelling with every passing second. This influx of energy was what stabilized its impossible path, allowing it to perform braking maneuvers that would have torn any normal comet or asteroid to pieces. It was using Jupiter's own strength to tame Jupiter's gravity. Every complex equation that had attempted to model its path, equations previously riddled with error bars and statistical uncertainties, suddenly collapsed into a single, elegant solution. The final leg of its journey, which had seemed so precarious, was now revealed to be the most stable and predictable part of its entire flight. Once locked into this magnetic resonance, its trajectory became absolute, an unwavering line drawn towards a very specific destination within the Jovian system. It was no longer aiming for the planet in a general sense. The data showed it was vectoring towards a precise Lagrange point, a pocket of gravitational stability nestled between Jupiter and its inner moons. It was a destination chosen with the precision of a surgeon, a cosmic harbor it had spent millions of years navigating the interstellar ocean to reach. The mystery of its aim was solved. It wasn't a collision course. It was an arrival. It wasn't a random encounter. It was an act of deliberate physical convergence, orchestrated by laws of physics we were only just beginning to comprehend. The object was a natural machine, an interstellar messenger, and it had used the largest planet in our solar system as its final braking gate and its power station. The revelation was staggering, overturning decades of planetary science in a single afternoon. We had always viewed the cosmos as a place of grand but blind forces, gravity, radiation, orbital decay. We looked for patterns in the chaos. But 3I, Atlas, demonstrated a level of physical synergy, of environmental interaction that bordered on the biological. It was an object perfectly adapted to its task, its very composition designed to interface with its destination. It was as if a seed had been floating on the solar winds for eons, carrying within its core the precise genetic key needed to unlock the life-giving energy of a distant star's most powerful guardian. We had been asking the wrong question. We had been asking times why, times it was aiming for Jupiter, as if it were an anomaly, a mistake in the cosmic code. The data from Kronos forced us to reframe the entire puzzle. The question was never why, the question was how, and now we had the answer. Its unique crystalline physiology was the how. The why was its purpose, its function, a secret it had carried across the light years. And with its trajectory now locked, its power reserves brimming with the stolen energy of a gas giant, it was finally ready to reveal that purpose. Our visitor had arrived not by chance, but by design. And as it settled into its calm gravitational harbor, the silence that fell upon the scientific community was one of profound, terrifying, and beautiful anticipation. The real story we now understood was only just beginning, and there it was. Not with a clamorous bang or a blinding flash of insight, but with the quiet, elegant click of a cosmic tumbler falling perfectly into place. For years, 3I, Atlas, had been a ghost in our telescopes, a celestial enigma defying every neat explanation we tried to impose upon it. We saw its path, a line drawn with impossible purpose, across the void aiming for Jupiter with an unnerving precision that felt less like physics and more like fate. We chased its shadow through reams of data, building and dismantling theories with the frustrating rhythm of a tide. We argued it was a comet fragment, a bizarrely shaped asteroid, a piece of something much larger, shattered long ago. Yet each hypothesis crumbled under the weight of the object's sheer strangeness, its refusal to conform. The solution, when it finally coalesced from the painstaking work of hundreds of minds across the globe, was both more subtle and more profound than any of our wilder guesses: the gravitational siphon. A concept so elegant, so deeply embedded in the mathematics of space-time, that its discovery felt less like an invention and more like a memory of a truth we should have always known. Looking back now, the journey to that truth is a testament not to a single spark of genius, but to the slow, grinding pressure of relentless human curiosity. It's a story written in the faint signals from distant antennae, in the low hum of supercomputers, running simulations through the night, and in the faces of scientists illuminated by monitor glow, chasing a ghost across the solar system. We remember the dead ends, the months spent pursuing orbital resonances that led nowhere, the tantalizing chemical signatures that turned out to be instrumental noise. Each failure was a stepping stone, a necessary sacrifice on the altar of discovery. It was a global endeavor, in the truest sense, a conversation held in the universal language of mathematics and physics, transcending borders and time zones. An observation made from a Chilean mountaintop one night would become the critical data point for a theoretical model being built in Germany the next morning, which was then refined by a team in Japan before the sun had even set in Santiago. This was not a race, it was a collaborative ascent of a mountain no one could climb alone. The process itself was a kind of alchemy, transforming disparate, chaotic threads of information into a single cohesive narrative. Imagine the challenge. You have fragments of light spectra, blurred by interstellar dust, and Doppler shifts measured to infinitesimal degrees of precision. From these cosmic breadcrumbs, you are asked to reconstruct the entire life story of an object, billions of years old and trillions of miles from its origin. It required a symphony of technologies, from the powerful optics of ground-based observatories that first flagged the object's oddness to the space-based telescopes that gave us an unblemished view of its faint cometary tail. It demanded new computational algorithms, predictive models so complex they could simulate thousands of potential gravitational encounters at once, searching for the one specific pathway that matched reality. The teams had to teach their machines to think creatively, to consider the improbable, to look for the subtle gravitational handshakes between 3i, Atlas, and the giant planets of our own solar system. They had to account for the gentle, persistent push of solar radiation, the minute outgassing from its icy core, and the echoes of gravitational nudges from stars it passed millions of years ago. It was the ultimate forensic investigation, with the crime scene spanning light years and the only evidence being the faintest of celestial fingerprints left on the fabric of space-time. What we celebrate, then, is not just the answer, but the sheer indomitable power of the scientific method that unearthed it. We celebrate the graduate students who sacrificed sleep to recalibrate instruments, the seasoned professors who challenged their own long-held assumptions, and the software engineers who wrote the code that allowed us to see the invisible. This discovery is their monument. It stands as a powerful rebuke to the notion of the lone genius. Instead, it is a testament to a connected collective intelligence, a global brain tackling a cosmic mystery. The answer wasn't hidden in a single observatory or a single equation. It was distributed across the entire network, waiting for the right questions to be asked in the right sequence. The story of 3i, Atlas, is a profoundly human one, a story of persistence over frustration, of collaboration over competition, and of our unyielding desire to understand our place in the cosmos, to make sense of the silent visitors that drift through our celestial home. It is a reminder that the greatest tool of discovery we possess is not a mirror or a lens, but the shared network of inquisitive human minds working in concert to pull a single shimmering thread of truth from the infinite tapestry of the stuffing universe. And the truth we have pulled is one that fundamentally reshapes our understanding of the cosmic neighborhood. For so long, we viewed interstellar objects like Oumuamua and Borisov as mere curiosities, vagabonds cast out from their home systems by gravitational chaos, tumbling randomly through the void. They were fascinating, yes, but they were seen as isolated statistical flukes. 3I Atlas changes that perception entirely. The gravitational siphon mechanism it has revealed suggests something far more orderly, a hidden architecture of connection between star systems. It implies that gas giants like our own Jupiter are not merely passive residents of their solar systems. They are cosmic anchors, gravitational lighthouses that can actively shape the trajectories of interstellar travelers. They create subtle, intricate corridors through space-time funnels that can gently capture and guide objects that happen to approach with just the right velocity and angle. This isn't a violent, dramatic capture. It's a soft, almost imperceptible redirection, a slow dance of gravity playing out over millennia. This discovery forces us to ask a startling new question. Are some interstellar objects not random wanderers at all, but natural probes, unintentionally directed towards systems with large planets? Think of it. An object is ejected from its native system, sent on a journey into the dark. For millions of years, it travels its path, dictated by the simple, lonely mathematics of inertia. But as it nears a new star, one with a massive gas giant, it enters a zone of influence, a gravitational watershed. If its trajectory is just right, it can be drawn in its path, bent from a straight, lonely line into a graceful, sweeping arc, a path of investigation. Jupiter in this new picture becomes a kind of cosmic fishing net, passively but effectively collecting samples from the interstellar medium. The implication is staggering. It suggests that the space around gas giants could be disproportionately rich in material from other stars. These worlds may act as celestial archives, collecting and preserving chemical and geological messengers from countless other solar systems over billions of years. We may have been looking for alien artifacts in all the wrong places. Perhaps the most valuable extraterrestrial samples we will ever find are not metallic ships, but the icy, dusty bodies that have been naturally delivered to the doorsteps of our own outer planets. This reframes the entire purpose of planetary science. Missions to Jupiter and its moons, like Juno and the upcoming Europa Clipper, suddenly take on a new and profound importance. They are no longer just exploring our own solar system's history. They may be on the verge of becoming interstellar archaeological digs. Imagine analyzing the dust in Jupiter's rings, or the cryovolcanic plumes of its moons, and finding isotopic ratios or mineral compositions that are utterly alien to our own nebula. We could find ourselves sifting through the chemical building blocks of a completely different world, a world that circled a different sun. Each piece of captured interstellar debris becomes a time capsule, carrying information about the chemistry, temperature, and dynamics of its place of origin. It is the ultimate form of remote sensing. We wouldn't need to send a probe light years away to study an alien planet's environment. The universe, it seems, might be delivering samples directly to us, using the elegant physics of gravity as its courier service. The legacy of 3I Atlas is that it has given us a treasure map pointing to the outer solar system as a potential library of galactic information, with each captured object a book written in a language we are just now learning to read. Beyond our own cosmic backyard, this discovery provides a powerful new lens through which to view exoplanetary systems. As we scan the heavens with telescopes like the James Webb, we detect thousands of distant worlds. We can measure their size, estimate their mass, and even analyze the chemistry of their atmospheres. But understanding the dynamics of those systems, how the planets interact, how stable their orbits are, what kind of debris fields they contain, has been incredibly difficult. 3I Atlas offers a revolutionary new tool. It was, in effect, a messenger from its home system. Its trajectory, its speed, and the subtle gravitational scars it carried from its ejection told us a story. By reverse engineering its path, by tracing its journey backward through time, we can infer the architecture of the system that threw it out. We can hypothesize about the size and location of the gas giant that must have acted as the gravitational slingshot. We can estimate the mass of its parent star. Suddenly, an interstellar object is no longer just a rock. It is a fossil record of planetary dynamics. Every future interstellar visitor we detect will now be scrutinized in this new light. We will not just ask, what is it made of? We will ask, what story does its journey tell? By studying the distribution, composition, and trajectories of a multitude of these objects, we could begin to build a galactic atlas of planetary system architectures. We could learn which types of stars are most likely to eject material and what that material typically looks like. We could compare the chemical makeup of rocks born around red dwarfs to those born around sun-like stars. This is no longer science fiction. We would be performing galactic geology by proxy. Using these travelers as our probes, each one becomes a precious free sample, a chance to touch a piece of a world we can never visit. 3i, Atlas, has transformed them from points of light into data-rich packages, each one holding clues to the great cosmic lottery of planetary formation. It has given us a way to study the diversity of solar systems, not just by looking at them through a telescope, but by sifting through the very material they have shed into the galactic tide. And so the hunt is on, but it is a hunt transformed. We are no longer simply scanning the sky for anomalies. We are now searching with purpose, armed with a new predictive model. Observatories of the near future like the Vera C. Rubin Observatory in Chile are designed to survey the entire sky every few nights. They will generate an unprecedented river of data, and within that torrent, we now know what to look for. We can build algorithms specifically designed to flag objects whose trajectories suggest they are not just passing through, but are being actively guided by the gravitational hand of Jupiter or Saturn. We can prioritize these targets, directing our most powerful instruments to study them in exquisite detail before they swing back out into the darkness. We have moved from being passive observers of the interstellar traffic to active participants capable of anticipating the arrival of these crucial messengers. This is a paradigm shift in astronomy, a move from reactive discovery to predictive science. 3i, Atlas, has provided the crucial Rosetta Stone, allowing us to translate the subtle language of orbital mechanics into a forecast of future discovery. The journey of 3i, Atlas, from an enigmatic blip of light to a key that has unlocked a new understanding of the cosmos, mirrors our own journey of discovery. It began in darkness, a solitary traveler on an incomprehensible path. Through the sustained, focused light of human inquiry, we illuminated its nature, its history, and its purpose. In understanding its trajectory, we have altered our own. We now see the universe not as a collection of isolated islands, but as a vast, interconnected ecosystem bound by invisible rivers of gravity that ferry material and information between stars. 3i, Atlas was the first vessel we saw navigating these currents, but it will not be the last. Its enduring legacy is a profound sense of anticipation, a thrilling awareness that the sky above us is filled with more than just light. It is filled with stories, with chemical histories, with the physical remnants of distant worlds, all waiting to be read. The great silent darkness is not empty. It is simply waiting for us to learn how to listen.